Welcome back, ladies and germs, to the One Deeper podcast. This week, I have Dr. Jeffrey Evans. We talk about computers, where they came from, how they work, why we need them, all the good stuff. So, if you're interested in figuring out the nitty gritties of why computers do the things they do and why we use them so much, stick around. I hope you learn something. It's always a pleasure to talk to Dr. Evans, and so please enjoy this conversation. All right, cool. So basically, this is like the idea I had was this, right? So we had we had a really nice a cognitive neuroscience course, right?
Uh-huh.
Which had a big biology component, about how cognition and intelligence works in humans, right? And I was like thinking we need like okay, so we learned about the substrate that the biological intelligence that we're working on has, uh, but I wanted to like just do like a real, as much as we can do on a conversation, but like something from like basically the questions I asked you, right? Like memory, processing, uh,
Hmm.
and the like. So like why things get weird when you go much smaller than a certain distance. Like why you can't make electronics smaller after a certain point because of electronic the electron stuff, such and such. Okay, it's up to you honestly, because I have no idea what I'm talking about. Like I mean, I have some idea, but what do you think would be a nice place to start, like from the lowest level and then work up? Because like I'm thinking like transistors and how they work, and then memory and the communication between the memory and the processor and what is actually happening. I don't know. I just have a bunch of questions. I haven't really, you know, uh,
Well, and I'm looking at the email um, that you wrote me about this particular podcast, and
yeah,
you the first sentence talks a little bit about history,
yeah, that'd be
uh,
nice.
about what computers used to be and what they are today,
Yeah,
and then you get into like what is a CPU, what is memory, what is data, how is it represented,
yeah,
um, some conditions, um, cache, that kind of stuff. And then you ask the question, what is a GPU? How is it different from a CPU?
yeah,
Um, how does a CPU interact with memory? What is quantum computing? So you're kind of going in sort of a historical order,
yeah.
um, looking forward, right? So you kind of we look back and then we look to kind of what is now, and then you mentioned quantum computing, um, and so we can touch on a lot of those things. um, if
Okay.
it makes sense, maybe we talk a little bit about history, because a lot of this stuff with the fact that transistors have gotten smaller and all that kind of stuff, um, kind of doesn't happen without some kind of need for it to happen. In other words,
Hmm.
why do we need these things to get smaller, and all of that kind of stuff? What's wrong with what was wrong with the Intel 8080, which was around in the late 1970s?
Right.
Um, why aren't we still using those things? So we can talk a little bit about a lot of that stuff, because fundamentally, I mean, the basics of a CPU really haven't changed all that much.
Right.
Um, the notion of a GPU came about because the technology for displays, what we saw on a screen changed. Computers went from being things that were that primarily displayed text to things that primarily started to display graphics.
Yeah.
And so technology changed to the point where, gee, we needed more horsepower to keep up with the fact that you had a lot more pixels on the screen, and we started moving those pixels faster.
Right.
Games, that kind of stuff. We turned computers into television sets, basically. Um, so there's a lot of reasons why things kind of evolved. Um, so how would you like to, how would you like to begin? Because I mean,
Yeah. 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 Okay.
I experienced this almost from the beginning. It wasn't from the actual beginning of computers. I'm not old enough to be around in the 1940s and 50s, early
Right.
50s, when the first large machines were constructed. But I was there when the first PCs came about.
Right.
And those were with very, very, what would be considered, ancient, slow, whatever microprocessors with no graphic. No, there was no such thing as a GPU, right? Um, and in fact, there was no need for things like memory hierarchies with cache and various cache levels and that kind of stuff. I
Right.
mean,
Right.
so um, I mean, in that day, again, displays were text based, so they didn't have to get refreshed very, very often.
Hmm.
Compute, the microprocessor was an 8-bit machine um, that, and I thought about this a lot when you asked me about what is a CPU. Um, the first class that I took about microprocessors was, I don't know, in 1981 ish. And the instructor, the professor, is a brilliant guy. He basically said, CPU is nothing but a state machine.
Hmm.
And now it's 45 years later, and I went back and thought about this and went, wow, you're right. It's nothing but a state machine, right? You
Right.
give it some inputs. The transistors are constructed in such a way, the gates and all that kind of stuff, to take that information and then transform it into some kind of an output. It's a state machine, and it's working with ones and zeros.
Right. 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 So
So,
actually, wait. So this is interesting, right? So like this, so one of the things I've learned, what I realized is when the representation to a how you represent the thing you're trying to work with is super important, right? Like if you're trying to process an image, what is the appropriate representation of that image for your problem, right?
mhm,
And I was just thinking, like, okay, anything you put on a computer uh, is just like, so for example, an image on a screen, when we look at it, is a pixel map of intensities, right? Fair enough, right?
mhm.
But then on the hardware, on the memory, it's just a collection of on-off states of the physical machine, right?
Right.
So, but working with that representation might not be useful because it doesn't actually hold something. I find that unbelievable, and like it's crazy because like on the memory at the memory hardware level, it's atoms and bits, right? Or whatever I say, atoms,
Mhm,
like electrons, whatever it is, right?
mhm.
But at that level, it has absolutely no representation of the spatial and the color and the actual image that we care about.
Correct.
right?
It's a it's a it's a it is a complete human generated mapping
Yep.
from those ones and zeros to something that your eye perceives
Right.
when we're talking about graphics, for
Yeah. Yeah.
example. And the best example right now today is are the things like the last two big space telescopes, Hubble and Webb,
Mm-hmm.
right? They are looking at infrared energy. So we can't see that.
Right. Right. Right.
So the images that we see, the scientists have taken all of that data, right, which is infrared,
Right.
energy, which is then mapped
Right.
into
Right. Right.
some kind of data, and then they transform it into something that we as humans can then look at and go, oh wow, that's amazing,
Right.
right?
Yeah.
So presumably there's enough. I don't claim to be an expert or any. I'm not even a novice, right? I'm
Yeah.
just completely naive, right? Um, there must be some research that has been done such that certain wavelengths in the infrared spectrum can transform into other wavelengths in the visible light spectrum
Mm-hmm.
that make sense,
Right.
right? That so whatever it is in infrared ends up looking like blue or green or whatever,
Right.
to the human eye. So that transformation has to happen from the raw data that's coming from the telescope.
Right.
So
Right.
your point is what is perfectly well formed, right? I mean, this stuff starts off as and again, I'll go, I'll date myself, go back into the old days, right? We created things like, the ASCII table. So 8
Mm-hmm.
bits of information represented a capital letter A, a capital
Right.
letter
Right.
B, a small letter, and then it grew to where now we have other languages represented by those same keystrokes,
Right.
right? So you can have, yeah, in various, countries, a keyboard might look a little bit different, right? With the graphic that is on a particular key, but that data representation in the right organization, you can construct sentences and you can do all that kind of stuff,
Right.
right?
Right.
So there's this constant mapping of bits of ones and zeros, which are organized in memory, which are operated on by the CPU, okay, to then come, be output into various forms that we basically can understand, whether it's written language, graphical representation, audio comes into the same, comes into the same genre. In other words, there's rule sets for what makes up how digital audio is represented by data or put on media
Right.
in order to either stream it or put it on CDs or what have you, right?
Right. Right. Yeah. So, like, okay. S- so figuring out what level of that representation stack you should work with, like, it's like the more you look, the more you know, the more you're like, Jesus, man, like, where is the information really? Like, where does it actually exist, right? Like, obviously, when we see something and when we perceive audio, we hear music, we like it's sent through the bottleneck of our input channels, right? The vision, sound, whatever it is, we have, like, we limit. No, one of the most amazing things I've ever read uh, was Aldous Huxley's description of a mescaline trip, right?
Uh-huh.
And he describes the physical senses of the human body as a reducing valve, which basically eliminates almost all information and just retains the things that we absolutely need to exist and survive, right? So we don't see reality as what it is, but just what we need to exist, right?
Yeah.
So like, because I took this computer vision class which completely rocked my world. and and I was just like, I like after the like 13 weeks of that course, and I was doubting what like I couldn't even trust my own senses anymore because I was like, what is the world really? But anyway, we're getting in the weeds, right? Weeds
No,
here.
but those are good questions,
Yeah,
right? Because all of this starts somewhere,
right.
right? I mean, we represent pixels, a pixel element on a screen by its color, its intensity,
Hmm.
all that kind of stuff. And again, like in the old days, well, it was like an 8-bit representation. Well, now that thing has expanded, to 24, 32, whatever it is today,
Right.
and now you're working with 4K. Now we're going to 8K.
Yeah. Yeah.
So just do the math.
Right. Right. Right.
Right? And the frame rates used to be 24 frames per second, which your eye basically has a tough time keeping up with.
Hmm.
And now with games and all that kind of stuff, we're now at 8K, 120 frames per second.
Yeah. Yeah.
The math to make that happen,
Yeah.
right? It's a lot of data that has to get sent to the screen
Yeah.
really, really quickly.
So
And
the like I used to think I was like, man, spending all this money on TVs was a waste of like because people like buying new TVs, right? But now I'm like, man, how do they like? I go to the store, I'm like staring at like these insane screens, and I'm thinking like just like think about all the stuff that I learned. I'm like, how is this happening? This is preposterous. The fact that you can
right,
build this thing, right? It's insane.
right. So you'll get to a point if you haven't already,
Yeah.
right? Where and I used to be in the telecommunications business,
Hmm.
right? So I understand how internets work. I
Right.
understand um, from the basic signal levels on a fiber optic cable all the way till now you and I can have this conversation and it's live video from halfway across the planet.
Yeah.
Okay. And I am still amazed to this day that any of it actually
I
works.
know it's insane. Like so because so this summer I was a software engineering intern, right? And like uh, the product super straight like from the customer's point of view, super straightforward. It lets you do send surveys out, get information, collect information,
Yeah.
like build the data, everything, right? And I
Hmm.
was like, huh, pretty cool, right? And then I joined the engineering team, and I was just like the entire like the entire time I was mostly just like this, like what? Because the number of internal parts that have to work to make this all like so it's like I mean this is simple to say, but like it's like when you're a customer, especially of these high tech things, you see the iceberg, right? Like you see Netflix playing this. You see the top of the iceberg. You see the Netflix video playing perfectly, like it's totally cool. But
Hmm.
then once you start to like look behind the curtain and look at the architecture and the services behind it, and you're like, Jesus, man, how does any of this ever work at all? Like it makes no sense because
Right.
the default setting of the world is for things to not work, right? Like that's the default, like the default state is like just atoms everywhere, and like it's not in any meaningful configuration, and it's just a mess. Like nothing works, everything's cold, and like so I'm reading this book by this physicist right now. It's amazing. So like because for example, like if you think of like space, you tend like the average person usually thinks of space like full of stars, like sun, like bright, but that's not what space is. Most of space is cold, it's empty, right? It's
Yes.
and it's black. Like if you go to like the average position in space, you don't see any stars because they're so far away. A star could explode, could supernova, and you still wouldn't see it because it's so far away, and it's like 4 degrees Kelvin, right?
Right.
And it's absurd. And then you come to planet Earth, and we have this insane concentration of things that work, doing things that in some structured manner, all put together by people who are like, you know what, this sucks, let's fix it. Right.
And go even further, um, take humans out of the equation.
Yeah.
Look at what look at what insects and other
Oh yeah,
animals
yeah, yeah,
like
absolutely.
that. Look at what they can do.
Yeah, it's insane.
You know, I mean, their worlds operate just fine,
Yeah, yeah,
and they have their own technology,
yeah, yeah,
right?
yeah.
Whatever that is.
Like ants are an amazing example of this. Like ant farm, like have you seen those like ant things on the ground? They're insane. I have like
Yes,
pre- preposterous. Okay, okay.
yes,
So look, okay, we've got okay. Look, so one interesting thing I realized also is like in terms of computers.
yep.
So for example, gradient descent, right? Probably like the black it's like it's an algorithm that's like the backbone of I don't know if you know about this, but like it's the backbone of most learning algorithms, right? It's the mechanism by which you update the parameters of your neural network, let's say, based on the examples it sees, right? So
Mhm.
you give it an example, then you take a bunch of derivatives and you update the parameters with respect to the loss, the cost, the mistakes that were made by the network, right?
Mhm.
Okay, so that was invented in the 1800s, like like 1857 or something. The idea of doing a gradient descent, right?
Right.
But we couldn't do anything with it until
Correct.
like what, I don't know, to 20, 30 years ago, when we could finally build neural networks that could actually handle and work fast enough or work with enough data, right?
Right. And even those that, from 20, 30 years ago were pretty primitive
Yeah, 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 yeah.
and slow,
Mhm.
right? And, kind of cumbersome, that kind of thing. So, all of this continues to evolve, and as it does, um, hopefully new knowledge, whether it's in fields of artificial intelligence or machine learning or what have you, kind of come to pass. And that's why I think what you're doing is so important, right? Because you're trying to make sense out of not only all of this, computational, capability, but also, the human element, right? The,
Mhm.
the the human cognition element, the ethical elements, the
Yeah,
moral elements. What makes this stuff. Just because you can do certain things, is
yeah,
it the right thing to do?
yeah.
Um, and again, sadly, because we developed these computer things, there are elements that will misuse or abuse technologies, for purposes that aren't that beneficial to
You
humankind.
know, like one of my motivating drivers to like to get to understand this stuff and to learn this stuff is so that when it comes down to it, like I want to be good enough that someone can ask me to do something terrible, and for me to be able to say no, I'm not going to do that, right? It's
Well,
like
right.
if so someone's like, hey, I want you to build this thing that's going to do, like, I don't know, this awful thing. Like I want to be competent enough for so that they come to me and then I get to say, you know what, no, I don't want to be involved in this, that's not something I want to
Well, right. I mean, think about I mean, you know, the Oppenheimers and the Fermis of the world knew pretty well
do.
what they were doing when they were doing it,
Right.
and they understood what the ramifications could be. But again, now we're on the brink of fusion,
Mm.
which is it'll be tremendous if we can harness that. It will be absolutely tremendous.
Yeah, it would like solve, I mean, energy is like,
A lot of that,
yeah,
yes, a
it's insane.
lot of that will be, it'll be frankly pretty much solved. Which is it's
Insane, right? Like that's like so. I mean, so, part of the reason I think it's important to, so a lot of people are terrified about a general intelligence, right? Like AGI or whatever, right?
sure.
But like I like okay, and some of my professors actually don't want to even talk about this because like not because like they think it's bad, but because it's like they think it's so far fetched. Because I get it, right? Because as I'm learning about these AI tools that I'm using right now, they're
Hmm.
really isolated, domain specific, like very narrow things, and it's hard to see how you go from this to something of sort of a general intelligent thing, right?
Right.
But like my thinking is okay, so I'm probably the kind of person who's like who's you know who I understand the reservation. Let's say it's possible, right? Let's say it's possible. My thinking is like we sort of like what if like do you want to wait or like, do you want to wait around for the luck of the draw for like for next Einstein or the next like fill in the blank, right?
Right.
Turing or anyone. Like we need a mechanism to build scalable, intelligent things to solve even so to solve problems that we don't know we have, right? Like we might need a fourth generation AGI to like find hacks into physics, right? To be like, you know what, you guys are limited by the way you see the world, so but from this perspective you can actually break physics in these weird ways and it does these things. Like it's I mean, that's like sci-fi weirdness in my head, but like I think there's a good reason to want to build an intelligence like that, right? Because there are problems that we desperately need to solve, like cancer, or like or even like very simple things, but like energy, for example, how
Hmm.
to uh, do these things like scalably, not just like make them do the scientific breakthroughs, but to make them production level scalable technologies. That, by the way, is probably the hardest thing. Like I learned that like doing something in the lab is not the same thing as putting it in the world, because it has to work reliably, it has to work safely, and it has to like do what it says it's going to do. And then when it's not doing it, you have to know why it's not doing it, right?
Right.
Like that's those three things are like
And that is what
Jesus.
makes software development to this day, right?
Yeah, yeah,
It's
yeah.
sort of a backward, um, it's sort of a backward field,
Hmm.
because again, we end up with corner cases that are either, well, we end up with corner cases that become very difficult to test and very difficult to recreate.
Hmm. Yeah, 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 for sure.
So whereas with a lot of things, um, I'll just use the hardware, domain, because I was a hardware designer for a long time. You could play statistical games because, like you say, things need to work reliably. If I'm selling 50 million smoke alarms over the course of 4 or 5 years, um, false positives can be tolerable, but false negatives kill people,
Right, right, yeah, for sure.
right? So,
Exactly.
so something silly like a little resistor or a capacitor or something like that. I mean, you're talking about millions and millions and millions and millions of these things working correctly all the time. Okay, seems straightforward,
Yeah.
but sometimes it's not. So, and because you get into, it's kind of the definition of engineering. It's trying to solve a problem, right, in a reliable yet economical way. So now you've put two constraints that sort of are in conflict,
Yeah, yeah, yeah.
right? So We used to have the old saying, right? Do you want it done? You want it done right? You want it done quick? Um, what was the third one? Oh, or you want it done cheap,
Mm.
right? Pick two of the three.
Right, right,
It's
right.
very, very difficult to get all three,
Yeah,
right?
yeah, 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 exactly.
Um, so that's the dilemma. Whether and it's computers, hardware, software, the interactions. We've made software almost to the point where between libraries and new language paradigms and things like that, you don't have to understand that much
Hmm.
about what the hardware is doing. You don't even have to be a software engineer per se, and you can make stuff that works on computers,
Yeah,
right?
yeah.
Therein lies the problem that you just said, right? When something goes wrong, you need to be able to, if you don't understand why immediately, you need to have the tools to get you to the why,
Yeah.
and that's a critical thinking, problem solving, coupled with the training in software engineering or software development, that kind of stuff that get you there, um, so that you can be pretty good at it and put out products that are safe and are recoverable, right? So, um, yeah, unfortunately, we've gone through this thing with airbags over the last couple of decades in cars, right? There's millions of these things out there, and all of a sudden, whoops, there might be a problem where a sizable number of these things can fail, and a false positive can be dangerous.
Yeah.
Yeah, yeah, so um, all these things, by and large, they work, but then when they don't, we sort of get kind of all up in arms.
It,
Yet we'll get on an airplane where we know that if that airplane goes down, the results are really bad.
I don't
You
like honestly. If I had worked on the stuff you had worked on, like smoke alarms, I don't know how I would have slept at night. Like,
Yeah, I mean, there were times. Well, every October,
yeah,
okay, and this to this day, October in the United States is Fire Prevention Month.
okay,
So there's this big, you hear about it on the news and things like that. Replace batteries in your smoke alarms, replace your carbon monoxide detectors, those kinds of things. Well, I designed both of those kinds of products,
hmm,
right? So when I see body bags on the news come out of a house, because of it was either a fire or there was a furnace that broke or something, and a family of 10, doesn't survive, the first thing that goes through my mind is, were there smoke alarms? Was there a carbon monoxide alarm in there? And was it receiving power when the incident happened? Right. Um, to this day, I think about that stuff. Yeah, because again, false positives can be tolerable, but false negatives are really bad. Um, so so yeah, I mean, those are, yeah, it's a, and at the time, um, we were designing these things so they could be, I don't know, $10, $15.
mm.
This is a thing supposed to save your life.
Right, right, yeah,
And and yet, people didn't want to spend, 50, 60, $70, for something like that intended to save your life, because it's a rare event. you know
yeah,
Fires
but
are rare
yeah,
events,
but
and
rare events have outsized consequences.
yes. So and now, we're, to keep the topic, with computers. I mean, at the time that the internet first began, Berners-Lee and those guys, they had no idea that this, all of a sudden, that this was going to be used for commerce
Hmm.
in the way that it's used for commerce today. Yeah, it wasn't in their thinking,
Yeah,
right?
like
So no,
scientists.
you don't think about security.
Yeah, scientists don't think, like, they're just driven by, hey, this is how does this thing work? Like,
All they wanted to do was send email back and
yeah,
forth to
yeah,
national labs,
yeah,
right? These are
yeah,
physicists trying to communicate with each other,
yeah, yeah,
right? Um, and so in the beginning it was just, oh well, we can do this, and we can do this network of different places around the world, and we can actually make this happen. How cool is that?
yeah,
Really neat, right? And
yeah,
again, the computer technology, it was all text based. There was no graphics involved, right? So it didn't need a lot of computational horsepower. It didn't need fiber optic communication networks to get information from point A to point B.
mhm.
In fact, if we could do, um, I remember my first job at Bell Telephone Laboratories, right? I had a 9600 baud modem, and everybody thought I was on cloud nine. 9600 baud. Think about that.
Yeah,
9600 bits per second,
yeah,
moving across some telecom line, um, and that was high end.
yeah.
That was like, man, that's like amazing.
That's crazy.
So it was, yeah, and in just a few short decades, we're at a gigabit per second coming to my house.
Yeah, and not even for like industrial stuff, just like casual stuff,
Yeah,
just to watch 4K Netflix, right? Like, it's fine.
right? Exactly. Exactly. So you have to ask yourself, as we keep going on these frontiers, right? I mean, the GPU coupled with advances in display technology was enough to offload the CPU, so the CPU could work on the game algorithm and the GPU could work on the graphics algorithms to make the guns fire and people move and the monsters and all that kind of stuff. Um, and an entire ecosystem, came about. And now we're doing it like you and I could play whatever kind of video game from halfway across the planet
Yeah,
in
yeah,
real time,
yeah.
which is kind of
It's
blows your
crazy.
mind, right?
Yeah, it's insane.
Right? So,
Yeah,
but simultaneously, we can use GPUs to help us solve other problems where basically the algorithm that either converts data or performs simple mathematics, right? Because computers still just do simple mathematics. They
mhm.
they add, subtract,
Oh,
multiply, and divide.
that's
That's
something
all
that
they do.
that's amazing. Like, that's what makes me like, like that's what gives me hope into like thinking, man, I can learn this stuff. Like, because computers fundamentally aren't doing anything that insane. Like,
Correct.
neural networks aren't doing anything that insane. Like, the technology, like the engineering is like phenomenal, is amazing, right?
Right.
But fundamentally, adds, subtracts, like,
Multiply,
but
divide. It's very simple.
from those
It's very
things.
simple stuff. Only they do it fast,
Yeah.
and because we've gotten to where the physics allow us to put multiple cores in CPUs, multiple cores in GPUs, things that lend themselves to parallel processing give us now this appearance that things are happening really, 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 really fast. And they
Mhm.
are, because we're able to parallelize them. Again, whereas historically, way back when, the only way you got things to operate in parallel was to have a desktop computer next to another desktop computer, and I connected them together and figured out ways to make the parallel pieces work on the two computers simultaneously while the stuff that had to happen in serial would happen later, right?
Right.
And we do that today. We do, supercomputers, right? Same kind of thing.
I mean,
um,
like the human brain is a massively parallel, really fast thing, right? But but much slower than a machine though,
yeah,
because it's still limited to those neurochemical transmissions, which are nowhere as fast as what a
correct. Well, it
process.
doesn't need to be,
Yeah,
right?
yeah.
The our senses only operate so fast.
Mm.
So the brain doesn't typically, it doesn't have to, you know, operate, for example, 1,000 times faster than it already does, right? I'm not certain. I'm not certain what benefit, if any, that would have,
Hmm.
right? Because your ability to, for example, why would that be a good thing? Well, maybe I could avoid an accident. Well, but if you still can't get your body, your muscles to do things right much faster than they already do, okay, then all of that processing speed doesn't necessarily help you. You just know you're going to die faster.
So so
Yeah, yeah, you know, um, yeah, yeah, so um, our senses, hearing, sight, touch, they operate on tens of milliseconds kind of time constants.
right. Yeah,
So
processes are
that's
like
that's
micro
kind of
milli. Yeah,
slow.
that's super
You
slow. Like that's so slow compared to a modern CPU or
Right,
GPU. It's so
right.
slow. It's like ancient time. So like one interesting thing which like idea is that, so let's say we do have an AI, right? And let's say we have to come up with something like the equivalent of a prison sentence for an AI, right? Like if you give it, like how do you scale the time, because it's built on the, on the hardware it's built on, it's way faster, right? So like
Hmm.
giving it like a 30-year life 30-year prison sentence would be like an eternity essentially, right?
Yeah.
So like anyway, that's a strange, the weird question, but like, but it is important. So I was thinking like, okay, if you're, because I always put these things in like in the AI context, because I find this in like it's insatiably satisfying to me, like to think about like this stuff. But so um do you think, like you just said, we have all these human limitations, right? Because of the substrate that we are made of, like we are like the biology and chemistry that limits our existence, right?
Right.
And somehow it's given rise to this intelligence that, let's say, right? Do you think the fact that computer like AI in the foreseeable future are most likely going to be built on silicon, that it's going to be something fundamentally different? Like, is it even possible to create a human-like intelligence on a substrate that's so different from the substrate that we are using, and a substrate that's also running much faster than than our hardware, right? So I don't know. I'm just like
Yeah. I mean, I think about, um, for example, how far the area of robotics,
yeah.
because there's a combination there. There's some AI things going on, and then the fact that the the robot, the machine, is trying to mimic um, human senses,
Hmm.
right? Sight, hearing, all that kind of stuff. Um, it can actually do a better job, right? I mean, we're building cars now that can see out, half a mile away,
Right.
that you're not, you can't even come close to being able to process and deal with that kind of stuff. So, okay, fine. And yet, Um, it's getting much better. It's getting much closer. But again, the scalability still isn't there yet for robots that have the same, if not better, dexterity, real time dexterity, than humans do, even though humans are slower.
Right, right, right.
Right?
True, 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 true,
So,
true, true.
so
Yeah,
yeah, the tasks of climbing stairs.
yeah, yeah, yeah.
I
It's
mean,
insane.
it's humans do it without second thought.
Yeah,
Whereas the robot and things like that oftentimes still looks a bit clumsy
yeah, yeah, yeah,
doing that. Now, granted, it's all gotten better and it's getting way better, but it's also expensive.
yeah.
That dexterity comes at a price. Um, so it's going to be. I'm intrigued by where all of this is going and to what, again, useful purposes. What are the useful purposes for humanity? Is it? I don't know.
Like studying AI has been an amazing path to sort of appreciate the the sheer breadth of things you can do as a human being. It's unbelievable. Like
Yes,
we take these things so much for granted.
yes,
It's preposterous. Like the fact that like like you just said, like walking up a staircase, like we don't even think about that, right? Or like riding a bike. Oh, no, no,
right.
just like when you're walking in an umbrella and it's windy, right? Dude,
Yes,
that, like I was doing it the other day and I was thinking to myself, how on God's green earth would I get a machine to do this? This is
right,
impossible, right?
right.
It's
Yes,
crazy, and I do it effortlessly. Like it's fine. I don't think about adjusting it. It's just like I just move it. It's
right,
unbelievable.
right. Your senses, um, and as you say, and I agree, are fairly slow
Yeah, yeah, yeah.
compared to computational power, but you effortlessly sense something happening, you respond to counter that thing to keep the umbrella balanced so it doesn't blow away, right? And you have just the right amount of muscular pressure that you apply,
Yeah, it's
to
crazy.
keep things balanced and all that kind of stuff. And again, you're not really thinking about it.
Yeah,
It's just happening,
yeah, yeah.
So yeah, it's way cool. I mean, think
It's
about,
it's nuts.
your studies and all that kind of stuff, and it's like, okay, there's seemingly pretty simple thing that again is pretty effortless,
Yeah,
you know.
I have an existential crisis at least once a week because I'm like, Jesus, man, like how am I supposed it's it's like how does this even work? Like how do you begin to conceptualize it in a in an engineering way? Like, okay, how do I don't even know what parts to start to break this up into to start working on it. Like it's like what are the parts even? I have no idea. Because like fundamentally you're like, okay, like like if just think about it, like I really appreciate the fact that like I have an engineering background, right? So like when I was in like so we had an ethics of AI course, and I was the only person with an engineering background in there, and I was just like I was like, I was, like I was always the person who's like, no, you know what, that doesn't make it. Like, look, that's a nice idea, but there's no way it's gonna work, right? Like, and they're like, yes, okay, fine, fair enough, but it's just a thought experiment. I'm like, yeah, but like, I'm just saying, I want to be on record to know as having said, this make any sense. But anyway,
I'm skeptical,
yeah,
right?
yeah, yeah. It's like, um, um, okay, okay, okay. We got super distracted, but great conversation. Okay, I want to ask. Okay, let's actually try and answer one of the questions that I asked you. Okay, so a CPU, right?
Hmm.
It's like if you were to build a CPU on a breadboard, what would it look like? Like if someone said, build me a proof of concept of a CPU, like what are the is it, what like is it, can you describe it? Is it possible to describe, in that way?
Yeah, I mean it's basically a large, a fairly large conglomeration of gates,
Yeah,
gates that perform logical functions
yeah.
and ors, that kind of thing, um, in concert with other structures that allow data to be kind of stored and operated on. In other words, I can add, subtract, multiply, divide, shift,
Yeah, yeah.
provide logical shifts,
Yeah.
right?
So, but like
Um,
fundamentally, is just doing a bunch of logical operations, right? Like, it's
yeah,
taking.
it's just doing a bunch of logical operations based on some input and a clock,
Yeah,
right?
yeah.
So I have this clock and something comes in and then the next clock something else happens, the next clock something else happens. You probably remember this from the old computer architecture course.
Yeah, yeah,
We
yeah.
went through that whole thing about what constitutes an instruction,
Mm-hmm.
right?
Yeah.
So things during the process of it, data has to be put somewhere in order to be operated on, in order for some output to happen. So now you get into this concept of memory,
Right,
right?
right, right.
So where, when the fundamental question to ask when an instruction starts, the first question is, where's the data?
Right,
Where is it?
right.
Is it right here inside the CPU so I don't have to do much? Or is it outside the CPU, in memory somewhere that I have to go get it and bring it in, operate on it, either leave it where it's at or send it back out,
So, okay, wait,
to.
okay. So, question. So, let's say the CPU is acting on some data, right?
Mhm.
Data is just, and let's say that data is in memory. Okay, okay. How is it stored in memory? It's like, what is the hardware implementation of memory? It's just, as far as I can remember, it's like it's just capacitors, right? Or like that, at least the random access memory.
Yeah, I mean, there are capacitive type of elements there. How memory is organized, um, there were primarily two rules of thumb, um, and it had to do with where the least significant bit was located versus the most significant bit,
Yeah,
right?
yeah,
Sometimes they're flipped around.
yeah, yeah,
So as long as you know that's that's kind of what the rule is. Okay, fine. You know, um, I get the data in and I operate on it. There are some subtle advantages and disadvantages to to you know data organized as most significant bit versus least significant bit. How the
and that
how
depends on the architecture of the hardware itself, right? Like it depends.
yeah,
Yeah,
yeah, yeah. So um, and so you have that, and then the notion of um, cache, right? We as computers evolved, the physics allowed for transistors to get smaller.
so what is the
So
transistor? First of all, what's the transistor?
it's just basically a switch.
Right. Yes. Okay.
It's basically a silicon switch,
Yeah.
right? If you play around with the silicon switch, so it's operating in kind of a linear mode instead of a binary mode,
Hmm.
right? Binary mode being it's either on conducting current or it's off, it's
Yeah.
not conducting current.
Yeah.
If I operate it somewhere in between, I make things like amplifiers and oscillators and things like that,
Yeah. Yeah.
right? So um, they're used for many purposes, but in the compute world, it's basically a switch. It's either on or it's off.
Yeah.
And so okay, fine. And I put all those things together, and we make out of a handful of these transistors, I can make a thing called a gate. So like a logical and. So I got two
Yeah.
inputs. If they're both in a given state, I get another state on the output,
Yeah.
right?
Yeah.
So, and now I use those as building blocks, right? And then I make larger configurations of these things, and before you know it, I've got a CPU,
Right.
a thing that
So the the logical operations that a CPU carries out are in a sense like universal logical operations, right? That's what.
yeah, it's based on Boolean, Boolean logic,
Right.
right? The things you can do with things in two states is
Right. So
either
that's why we could put a CPU in a Mac in this computer and do this stuff, or put it in a robot and do some other stuff, because like
correct.
the universal logic inside is built to do certain things, like to do certain
Yep,
types of stuff.
yep,
Nice.
yep. And it spans everything from computers to controlling the engine in your car
Yeah. Yeah.
to you know little control boards that control a furnace in a house,
Right.
to you name it.
So, but what enables the utility is that the at how fast it does these things.
Yeah, I mean, how fast it does what it does, how expensive it is,
Right. Yeah. Yeah.
right? How much, you know, these other peripherals, memory, that kind of stuff. I started to go into caches. That all came about kind of as a function of a couple of things, right? One, the hardware of the CPU was getting fast enough relative to the speed at which memory could be accessed
Mm-hmm.
to where the CPU hardware would have to wait. In other words, that instruction that we've been talking about. So where's the data? Well, it's out in memory. Well, now I have to wait for that data to come into my CPU, right? And that might take several clock ticks. So now basically I'm just waiting around for the data to come in before I can even operate on it.
Right.
So so that was a hardware limitation, but simultaneously we were learning about how software tended to operate.
Mm-hmm.
And there's this principle of locality and locality of reference, which you learned in the computer architecture course.
Can you remind
Way
me?
back when,
Yeah, way back.
right?
It's been a while.
Right?
Yeah.
So what we learned there is that in computer programs, oftentimes we will do a few instructions and then we will sit in a loop.
Mm-hmm.
We'll have this loop for X amount of times, do this thing. Okay. So the same memory locations are being accessed frequently in time, right? So now we could put faster memory up close to the CPU,
Mm-hmm.
and it would sit there and operate particularly on those loops, and then I wouldn't have to go out to the slower memory until something else happened.
Is it just the cost of time in going out to memory?
Primarily,
It's
yeah,
just the cost
yeah,
of
it's
time.
time,
Right. Right.
right? It was really just time. Um, so now you've got this, these various levels of cache. I mean, believe me, if Intel and Apple and the computer manufacturers of the world, if they did not have to implement cache structures in their computers, they would not do it
It's expensive.
because it costs money.
Yeah.
It's expensive. The faster the memory is, the more expensive it gets.
Yeah, but like also it doesn't matter how fast. Like okay, so like you can't just make a computer with just cache, right? Because just by the sheer fact that you have to place the hardware in a physical space, the further you are from the processor, regardless of how fast the memory is, it's still gonna cost you, right?
Well, I mean, the pragmatic answer is no, you wouldn't do that.
Yeah.
But in theory, you could build, a computer with like level one cache all on the same chip.
Mm.
It would be horrifically expensive,
Yeah. Yeah.
right?
yeah.
But it would be fast.
Yeah,
Uh,
but I guess like an average person, it makes for any like it doesn't make a difference. Like from like
well, and it would also be a little bit of a waste because of the principle of locality, right? That principle basically says you don't need that much,
mm,
high speed cache because that's not how computer programs work.
right. They work on
So
small bits of pieces of information at a time.
exactly,
Right. So they don't need the whole thing. They just need a little bit at a time. And we, as the users, as the humans, we get this. We get the perception of a continuous stream of things happening, like all
correct,
put together. But the processor, it's only working with tiny little pieces of a routine at a given time.
correct,
Nice.
correct,
Okay.
correct.
All right. So
So, and
yeah,
again, couple that with, again, historically, so you had memory doing its thing, you had display technology and other use cases for computers, i.e., games, um, i.e., from the scientific community, like um, large scale simulations that required
mhm,
lots of graphic detail,
yeah.
right? Um, so now we have this thing of, wow, the CPU really can't keep up with the operational logical tasks and the refresh rates and the data requirements to put the data on the screen.
Mm,
So we're going to make this other thing, call it a GPU, right? And you just look at the companies, right? NVIDIA didn't exist when Intel was developing its first microprocessors.
right.
Didn't exist,
Yeah.
right? So, it's been this evolution, in part because of use cases and in part because of technology, um, that made these things that we call GPUs useful. And in some cases now actually necessary. Some high performance computing systems, depending on what they're doing, they will use GPUs because they're highly parallelizable,
Mm,
um, instead of using CPUs
right.
for certain
So
functions.
from at least from like from our use cases, um, and so what I gather, if I was to if someone was to ask me, hey Udesh, all right, so what's the difference between CPU and GPU? Like all I can think of is matrix math. I would not do matrix math on a CPU. I would do it on a GPU, right? Because they say have a huge multidimensional matrix that I want to do a bunch of transformations on.
Right,
I because and just the way and how linear algebra is structured, it's a highly parallel operation, right?
right, right. And yet, when high performance computing systems were doing massively parallel, operations that required large matrices to operate on, okay, they were doing it with CPUs, and the computer language of choice was Fortran,
Mm.
and it still is
What?
to a large extent,
Why
right?
Fortran?
Because it lends itself to doing matrix math.
Oh, right. Okay.
It's really good at that. From as a computer language, it's just real. It was designed, in part for that
I've never
purpose.
used it. Like I've never.
Yeah. So it's the kind of thing I've programmed in it briefly when I was back in college. By the time I got to the supercomputing stuff that I was doing, the supercomputing research I was doing most of my work in C.
Mm.
So, but today now it's because we have this hardware technology we're calling GPUs that lends itself towards doing that multidimensional matrix math and that kind of thing. Now it makes sense. Definitely port it over there,
Mm.
and make it do its thing.
Right, right, right,
Um,
right.
and it works. I mean, when I remember this very distinctly, I was working at Argonne National Laboratories outside of Chicago, um, working on my doctorate, but I was using their facilities. And the Pentium 4 processor had just come out.
I remember those. Man, I was so excited to get. I was so excited to get one of those. Like
Okay.
oh man, yeah, it was nuts.
But the interesting thing was, so that we had this big Pentium 3 computational cluster
Mm.
that these physicists were doing high performance computing, algorithms and simulations and stuff on. And now we just built another Pentium 4 cluster, just as big, if not a little bit bigger. So the first thing these guys do is they take their code, they port it over to the Pentium 4.
Mm-hmm.
Okay. The algorithms were actually running slower. And the reason they were running slower was Intel decided to adjust the cache structure of how of the sizes of the cache levels
Right, right, right,
through
right.
through the memory chain,
Yeah, yeah.
right? That completely messed up the algorithms. They had to go back and redo them because the memory bandwidth was getting compromised
Right.
because those structures were different
So
now.
like so so they wrote it for they wrote the programs like they wrote the so when they wrote it on the Pentium threes, it was acceptably the speed was acceptable, and then they moved it to Pentium 4. They were like, what the hell? Why is it so slow? And then
Exactly.
yeah, it's because the architecture is different. But
Because the architecture had changed.
right, right, right,
And so now, they had to go back and change the algorithms to adjust the data structure sizes so that so that memory moving in and out of the processor
right,
would be better optimized. And once they did that, yeah, things got faster.
right, right, right.
But you can't just arbitrarily take something that has been really tuned, right, for one particular processor, one particular, processor architecture system, and then move it. Oh, this is the next greatest thing, right? We doubled the clock speed. We did all this other stuff, and all of a sudden, boom, the algorithm's running slower now.
Mm.
What's up with that,
Yeah, yeah, yeah,
right?
yeah, yeah.
So that is something that when you get into these highly specialized, kinds of algorithms, and I'm not an AI person, um, but it seems to me that over time this will be a thing. Um,
That's interesting,
you'll
actually.
have to
Like
look at that. You'll have to look at
yeah,
that. You
I
know,
hadn't thought about that. Like, so for the human intelligence, right? Like our hardware hasn't it doesn't change very often,
right?
right? Like our hardware is pretty fixed. Like I mean, it's not
Yep.
fixed. Like it takes a long time for it to change. But
Right.
computer hardware changes all the time. So like, let's say you build the intelligence, and then you're like, oh wait, now we have a new thing, and you try to port the intelligence to a new architecture, and it just doesn't work anymore. It's like
And
what?
you just broke
You
it.
just broke
Yep.
it.
Yep. And that has been happening. That has been happening historically.
Yeah.
So we're getting better at it.
Right. Right.
In working, with the various vendors and things like that when new systems come out and that sort of thing. But it's very important to have an understanding of, how those structures are kind of put together and why the vendors are doing what they're doing. And so you can say, okay, so this is what we have to tune to go from last year's, whatever to this year's, whatever, whether it's GPU, CPU, doesn't really matter.
Yeah. Yeah.
A lot of it comes down to memory bandwidth. Um, yeah, how fast can I get things in and out
Yeah.
of where I want to do the actual operations on the data.
Right, right. So this is so like one of the things Elon has been talking about with his Neuralink thing is he wants to open the bandwidth of the input channels because he finds his argument is that it's very limited, right? Like we have a very narrow bandwidth connected to this processor, right? But that seems a little bit insane because clearly the processor and the channels co-evolve together, right? It's not like this thing
Right.
came in and then we plugged in a couple of eyes and a couple of years, and the processing capacity is latent in there. It's like it's really
Right.
well tuned.
Right. Well, I mean, think of it this way. You've got two directions you can go. Really, only two. Right. You can either make things
Yeah,
faster by clock speed.
yeah,
Right. So instead of clocking at 1 gigahertz, I clock at 2 gigahertz.
yeah.
Okay. And or I make the input channels wider.
Hmm.
So I go from 16 bits to 32 bits
Yeah,
to 128 bits
yeah,
to 256 bits
yeah,
wide,
yeah.
right? So now I'm literally doubling, I'm doubling that capacity for the same clock speed by doubling the width,
Hmm.
right? Okay, that'll set up a new set of complications, right? Let's pick on graphics because that's near and dear to your heart right now.
Yeah.
Um, well, I mean, it used to be you had an 8-bit pixel.
Yeah.
Where are we at now? Are we at 32, 24?
Uh,
What's the norm?
I have no idea, but like it's
So we've gone by a factor of 3 or
yeah,
4
yeah,
on the width, which can convey a lot more information, between color and color depth
yeah,
and all that kind of stuff. And then somewhere in there, you've got to know where that pixel is located on the screen,
yeah,
right? Um, and now I've got to do it faster because I've got a 120 hertz refresh rate on a 4K screen. That's a lot of data.
yeah,
That's a lot of stuff, but it's pretty constant, right? Once I know that, right, my GPU, if you will, can be sort of fixed.
right, right, right.
I know that it's from one frame to the next. It's not all of a sudden going to be an 8K
Yeah,
thing. It's
yeah,
always going to be. I'm always writing to a 4K screen,
yeah,
so that's my limit. Yeah, so whereas a lot of the big problems, things where we're simulating things happening on the Earth,
yeah,
right?
yeah,
Um, we can continue to granularize them to where the scale needed in CPU, sometimes even GPU, can grow almost without bound. I mean, think about, for example, one of the easiest ones is like weather.
mm,
Okay, so let's take a square mile
yeah,
of land on the planet, right, and make some kind of choice. How far apart are let's use the term pixel, right? I've got a square mile. How many pixels am I going to put on that square mile, right? And now I'm going to go 40,000 feet vertical
hmm,
on that square mile
yeah,
and have all of those pixels going straight up, and they're all interacting with each other,
yeah,
right? I mean, and you know, you can take it. I don't know how far they go, but they probably go, 4, 5, 10, 100, interactions between these pixels, right? Um, to get to the point where you see the weather pattern happening on your TV screen on the evening news,
yeah, yeah.
right? Here's where the rain's coming. Okay. Um, so then you start asking the question, how granular do we want that to be?
Mm.
How granular does it need to be?
Like
When we study things like tornadoes and
yeah. So
hurricanes,
like
right?
at what resolution do you want to process this data?
Exactly. Exactly. And then how fast? Do we need this real
Yeah.
time? The simulation gets cranked out, and then okay, I've got this file, this model that's predicting the next 12 hours of what's going to happen. And by the way, you can get all this stuff on your iPhone.
Yeah, yeah, exactly.
Right? I mean, think about that for a
Yeah,
second,
yeah, yeah,
right?
yeah.
So now, granted, all it's really doing is projecting the output of that simulation. Here's the output that was generated in pixels, and this is what it looks like. And it's the good news is typically it's on a two-dimensional screen.
Yeah.
We're not trying to reproduce all three
Yeah.
dimensions,
See,
right?
so wait a second. Sorry, just a random thought occurred to me. Like, how would you keep a processor cool in a vacuum? I don't know why this came up, but I was thinking like, how do you? I was thinking about computers in space for some reason, and I was like, without conduction, like without convection and air, how would you keep a computer like cold? Wouldn't it just burn up?
Well, but what was the temperature that you said
Like
space
four
was
Kelvin,
out
yeah.
there? Yeah.
But like, how does?
What's the
And
problem? We're already there, right?
so wait,
Just put it out there.
so like my like I'm showing my complete ignorance of physics right now. But like, wait, hold on, because I was thinking like if the heat can't like so okay, when a process is working, how why does it generate heat?
Current flow.
Okay, but so now
We've got things
so
moving.
there
Atom, atoms are moving, or
right, okay.
subatomic particles are moving.
Okay, so that heat that we feel is just it's electromagnetic radiation, right?
Yeah, most likely.
So wait,
I guess
like no, because I was like,
we need Neil deGrasse Tyson here with
no,
us
no,
on this
no,
conversation.
because I was thinking like, okay, like if you have a processor in space and it's doing its thing, right? It's
Yeah.
generating like electrons moving around. It's still generating heat, right? But where how does the heat escape if there's nothing to conduct the heat away, like air or water? Maybe I just don't know.
Good
I have no idea what they are. Maybe I just don't know. I don't know what the hell I'm talking about. But anyway, because I wrote this really silly short story where
We know that it's worked historically because we put people on the moon.
that's true. Oh yeah, you're right. You're right. We have satellites.
So
We have satellites in space. Like it's
we,
clearly
we, we,
doable.
we know that we've done
Yeah,
at least that.
yeah,
So the archaic stuff that was done in the 60s and in early
yeah,
70s,
yeah.
we know that that kind of worked, and that was, pretty, you know, pretty early compute stuff. In fact, those quote computers were probably not microprocessors at all.
On the space shuttle, you mean?
No, space shuttle. The shuttle had, I think, it had some microprocessors on it, but it was very late in the shuttle program that they actually went to silicon memory.
Oh, okay.
They actually had, I don't know if you've ever seen it before, but the first memory was matrices of little toroids that were little rings
Okay.
that were around basically intersections of wire.
Okay.
Okay, and then they'd run current through it, and it would hold a state
Okay.
of a
So
one or a zero, and that was the memory. It was called core memory in the space shuttle. You can Google it and look
so
it
this
up,
is
and
this is this is a good point we came to. So memory. Okay. So why what does it mean when my computer says your memory is full? What does that mean? What's happening in there?
it basically means that
Like my RAM, like for example, like when I'm running something on my GPU or thing, it'll be like this memory is full. It can't like it's like get warning signs like it says.
yeah, what that means is you've done a poor job as a software developer.
All right, like
In,
let's put my crappy
right,
software engineering skills aside.
right, in cleaning up,
Yeah,
right, memory once your routines are
No, no.
basically
So
finished, right?
because I was TAing, I was a TA for data structures and algorithms, and so the
Yeah,
exam was a programming exam, and many like several students were like like their computers was freaking out because they were writing to memory to like variables that just kept blowing up because their code is terrible, and
yeah,
it was freaking out about
right,
it. Right.
right. And that's again, that's a thing that as we started the conversation, the computer's a really dumb thing,
Yes, exactly. It's very
right?
stupid.
If you keep filling up, RAM, it's going to let you do it until it can't,
Yeah.
right? And then eventually the operating system will notice that
Yeah.
and go, hey, I got nowhere to put this,
Yeah. Yeah.
basically. And so it is up to the algorithm, right? I mean, that was a huge deal in telecommunication,
Mm.
right? It was when checking algorithms for not only their function, um, we always had this thing we would test for what's called memory leaks,
Okay. What's the
right?
memory
And
leak?
a memory leak is just that.
Okay.
It's where memory is getting consumed to the point where we're out of it, and now you're stuck.
So what does it mean to consume memory? First of all.
Well, you're filling it up. You're basically assigning data to locations in memory.
So
Okay.
memory is just it's a charge state, right? It's holding a state of
Yeah,
electrical charge, right?
yeah,
Okay. Okay.
yeah. And it knows, basically the software, the operating system knows, okay, that this memory is being consumed, right? Um, I mean, the furthest storage element away from the CPU is the hard drive,
Right.
SSD, whatever it is now. Okay. Same problem, right? You can get into a situation where, hey, there's no more space on this SSD because you've consumed it all. You've put applications on it, you've put, all of your digital photos, all the data that you want to keep, it ends up out there and you fill it up.
Right. It's
Okay.
just a collection of each every time you put something on memory, it's like here are the specific states I want you of charge I want you to hold in this configuration.
Right,
Okay.
right. And as a software program, right, you have essentially kind of two choices, right? I either delete memory, I delete things that are
So what does it
there.
mean? So like what's the default charge state of memory? Like zeros? Like just it's empty?
Typically, it's
Ones.
ones.
Okay. Ones. Okay.
Um, and so the state then is, you're at the end of my program, at the end of my routine, right? I basically say, okay, I'm done with the memory that I've just consumed. So I allow the operating system to take it
Yeah.
back.
Yeah.
Okay. If I don't do that, the operating system doesn't know any better.
Yeah.
Okay. And it just says, oh, well, this part of memory is now consumed. It's being used. It thinks it's being
Yeah.
used.
So like some languages like Python will do that for you. It'll be like, okay, well,
Well, and that's the rub. That's where we've gotten to where, they used to say that about Java.
okay. Yeah.
Well, Java just takes care of
Yeah.
that
Yeah.
for you
Garbage collection.
until it doesn't, right?
Yeah.
And then all of a sudden things blow
Yeah. Yeah.
up,
Yeah. No, that
right?
happens all the time. Yeah, it's for sure.
Yeah. So it's like, and again, because I don't know if it's a good thing or a bad thing, because I grew up with these quote unquote primitive
Yeah.
languages, um, it was on us to, and primitive languages and very limited memory.
Yeah, 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 yeah. Like
Memory was
precious.
very
It's
sparse.
memory was precious,
Yes, it
right?
was
Like
precious.
you had to really think
It was
about what the hell you're going to do here. Yeah,
exactly.
yeah, yeah,
So when your routine was done, it was incumbent upon you to make sure that the memory was
yeah,
freed
yeah,
so
yeah,
it could be used by the next
yeah.
routine,
Kids these days are just
without
spoiled. We just put stuff in memory anywhere we want.
that. Exactly. And you can see what kind of problems that can arise, from
Yeah,
doing
so
that.
I took a C class this semester, but like I dropped um like it was a real philosophical thing for me because like it really makes you think like, is this absolutely necessary? Like, do I have to do this step? Like, because it's so annoying to get it to do something. Like, because like it's not like Python, right? You have to like say this is the variable. Here's where I want you to put it. Here's what I want you to do when you're done with it, and like do this thing, and then you're done. Python is like, oh,
Right.
it's like here, put me anywhere you want. Call me anything you want. It's all good, right? So
Right.
it's like going. So I was like, man, this is super annoying, but it's also it sort of forces you to really think about like your algorithms and like how you're storing stuff. Like, okay, do I want to put this
Yeah.
thing
I
here?
mean,
How big do I want it?
yeah.
Like, how big is my variable gonna be? Like, what do I expect it to? I mean, that's what makes it fast, right? Because you build in all that pre knowledge, like that pre existing knowledge about okay, this thing you're gonna get is gonna be a variable of this type. It's gonna be this
Yep.
big, so you can just when
Yep.
you get it, don't think about it, just run it immediately. Just do what I told you to do. Don't worry about what happens.
Right.
Yeah,
Right. And that again, that was it's a big deal when you are dealing with very limited
yeah,
memory. It's like, okay, this is finite. We have to um, we have to kind of cherish it.
mm,
So it's like, yes, we know that these, and again, when I was doing more software development, it was, you were picking, uh, you're very cautious about data
yeah,
types. Do I need, even if I'm performing mathematical operations, right? Do I need a double when something of length char
yeah,
will
yeah,
work?
yeah, yeah, yeah.
1 byte versus
Yeah,
4, that's a
it's a
big
big deal.
deal.
Yeah,
If especially if you're wasting 3 of the 4
yeah, yeah,
bytes.
yeah. So what do you do
So
with
yeah, that
accurate? Like how do you like? Let's say you want to store floating point numbers, right? I
yeah.
mean, doesn't that affect the accuracy? Like like the number, the memories, the size of the thing you like. How do you manage really accurate floating point numbers in a really memory limited environment?
It does get tricky,
Yeah,
right? I mean, we have done things where you're working with, for example, a single precision floating point number, which I think is 4 bytes, on an 8-bit
mm.
processor. How do you
I,
do that?
I don't
Now you
know.
now you start breaking it up into
Yeah,
pieces, and you have to keep tabs of, okay, what is it I'm dealing
yeah,
with?
yeah, yeah,
This representation isn't a typical binary number.
yeah.
It's another representation,
Right, right, right.
right? So it gets into that mapping
Yeah,
function,
yeah, yeah.
right? And if you're dealing in the digital signal processing world, it gets easier, but it gets harder.
Yeah, so computer vision is a big chunk of DSPs. Like it's a lot of
Yeah,
DSP.
because and on a lot of DSPs, well, today they're dealing with a lot more floating point, the IEEE floating point standard. But kind of back in the day, you were dealing with what they call bin point or binary point math.
Right.
So take your 8-bit number, right? 0 to
Yeah.
255, right? So I'm dealing with positive numbers
Yeah.
just for the sake of argument. Um, and now imagine, if you will, a binary point somewhere. within that 8 bits. Okay. So let's say move the binary point over 2 bits from the most significant
Yeah.
bit, right? So the largest number is 3.1/2 plus 1/4 plus
Uh-huh.
1/8 plus one,
Yeah.
right?
Yeah. 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 Yeah.
Okay.
Yeah. Yeah.
And now you can start doing mathematical operations on all that
Right. Right.
stuff,
Right. Right.
right?
Right. Yeah.
Okay. So again, it's coming back kind of almost full circle. It's the representation, it's the mental representation that you're counting on the physical computer just to perform this mathematical operation. But when it comes back out, I'm saying, oh, this is a bin point math number where the bin point is 2 bits over from this. So this actually represents this number,
Right. 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 So there's
right?
there's the representation. So there's the representation that you want, and the representation that you have to do the math on. Like it's
Yes.
two separate things.
Uh, yeah, more or less. Yeah, because again, the computer doesn't know anything about a bin
Yeah. It
point.
doesn't know. It doesn't know anything about math. Like it is.
Doesn't know
Yeah.
anything about it,
Yeah.
right? I mean, floating point units, floating point math units in CPUs are now better at they'll do an operation on two floating point math numbers and give you another floating point math number out,
Yeah.
right?
Okay.
So there was a time when we were doing some labs where I wanted students to do floating point operations, but without calling a number. You're doing it in C, right? Add these two floating point numbers, but you can't use IEEE floating point, right?
Okay.
You have to be the floating point
Oh,
processor,
right. Right. Right.
right?
Okay.
So, which is, again, to a student that's not used to that, it's kind of a mind blowing thing. It's like, whoa,
Yeah. Like.
how do I do?
So wait. I had a question. Something just came to my mind. First of all, how do you like? I had a question to ask, but it completely slipped my mind. But it was never mind. It'll come to me eventually.
Can we
Yeah, yeah,
pause
yeah,
for
yeah,
about 2 or 3
yeah, for
minutes?
sure. Yeah, I'm gonna
Okay.
pause. All right,
How do I do?
resumed. Okay, so memory. All right. Like I was just thinking, like I have this, like this is such a really interesting perspective for me to have because I have sort of like this full arc of like this knowledge. I mean, this interest slash knowledge, right? It's like now I'm learning about AI and the human brain and the cognitive, like very abstract cognitive stuff. But I also know a fair amount about the hardware on the brain, human brain, as well as like machines. It's really nice because like I can sort of see
Hmm.
like how the abstraction layers stack on one after the other after the other. It's it's super
Hmm.
interesting. I love that perspective. So like I can like see all the different layers of what it takes to do stuff in the world. So one of the things that, like you just mentioned, like one of the things I tell my students is like, listen, you have to stop thinking about the computer like another person. Like it's really stupid. Like it has no idea what you like. You can't interpret your intentions, right? So when you s- when your code goes wrong, the wrong question to ask is why isn't this working? Because it's doing precisely what you told it to do,
Correct.
right? So what did you tell it to do? Like that's the question, right? Is it like that's a big part of debugging like your code, right? um Anyways, okay. uh this is awesome. Like this is like these are the kind of conversations that really, man, it makes all this worth it. Like because like when I'm sitting around, like, so this, like, yesterday, like I spent like a good 3 hours yesterday literally just staring at the mathematical formulation of a loss function. And I was just like staring, because it's just this one line, right? It's just a line, but
Hmm.
it tells this insane story, right? It's like it's like here are the things that here the person that wrote it or created it, here are the things that I was trying to accomplish, here are the things that I care about, and here is how I want this thing to take something in, adjust those things, and then send something out again, right?
Hmm.
And like there's so like some like some equations or some formulas are so simple, are so elegant. You're like, oh, oh man, that's good. Like that's good stuff. Like I don't know how how did you, how on earth did you come up with this? This is preposterous. It's like it's so elegant. Like like for a simple logistic regression loss function, right? Like
Hmm.
to use the information like entropy and just like, oh, it's perfect, right?
Yep.
But like also like just the simple hardware implementation, like you said, right? The CPUs are just very simple like logic gates. But if you do things in the right order at the right speed, you can do insanely impressive and complicated stuff that just sort of emerge.
Right. So think about, um, and I think I probably mentioned this way back when you were at Purdue. Um, but think about the fact that, if one bit,
Yeah,
just one
yeah,
bit, one of those ones and
yeah.
zeros on one clock is wrong,
Mm,
okay? So, in the grand scheme of things, if we're just talking about data flying through the internet right
yeah,
now, right? What does that look like? Well, for your eye and my eye, we might not even notice
yeah.
it, okay? Get a few of those, and we might see a little bit of speckling, on the screen, okay? Do that at the right time inside the CPU,
Mm,
one bit, and all of a sudden your computer completely locks up.
right, right, right.
It
Yeah.
stops. It just stops working, right? So that's why I go back to it's a wonder that any of this stuff even works.
Absolutely. Like,
You know,
something that really, like, this is so simple, but like the fact that you can restart a computer is so useful. Oh my God. Right? Like, because it's just electrical states, right? It's just on off this thing. If imagine if they were like physical switches that like moved around every time you had to do something. That's it.
well,
Something goes wrong.
the
That's
very
it. Game over.
right, the very first computer that I operated on in college was just that. It was a
Yeah.
box that had a bunch of tongue switches on it, and you literally flip the tongue switches and then hit a button. That was the clock.
Yeah.
Click, flip them again,
Yeah.
click,
And the flips
flip
are
them
the
again.
instructions, right? The flips are the instructions. Yeah.
Yeah,
Right, right,
yes, you're giving it the
right, right,
instructions,
right, right,
and it's like, and then you'd see lights and things like that on the output side,
right, right, right.
So it was, yeah, that was, I feel ancient now, but that's kind of what we were working with. And then we graduated up to, oh, we're able to actually hook up a screen and a keyboard to this box
Right,
now.
right, right.
That was like, oh my
Right. So
gosh.
like in that box, it's like you have okay, you have a stream of input waiting to let's say it's like an array of input waiting for stuff to
Right.
happen. You have so you as the person, okay, you look at what data is supposed to go in next. When you adjust the adjust the switches accordingly,
Right.
saying on this data I want you to perform these operations and then give me the output,
Right.
and you collect the output
Right.
out somewhere and you do something with it.
Right. And the assignment that we got when we first got the keyboard and the display,
Mhm.
okay, connected to this box was program this thing so in the middle of the display it would simply count zero, one,
Yeah.
two, three, four, five, 7, 8,
Yeah.
9. Okay, that's all it had to
Yeah.
do,
Yeah. Yeah.
and the number was in the center of the
Yeah.
screen. You want to talk about something difficult,
Jesus, that sounds on.
because now we had to figure out where's the center of the
Oh
screen,
man, that's crazy. Yeah.
right? And then how to get something onto
Yeah.
it.
Yeah.
It
It was
was it
not.
was
That's
nuts.
that sounds
It was
insane.
crazy.
That sounds
It was
insane.
right, and that's all we were trying to
Oh my
accomplish.
god. No, like that
You
just
know,
goes to show like how grateful we have to be for the fact that all like the work that's been done way before we got here, right? Like now you can just now like my assignments, oh, build a neural network from scratch that can classify this image, right? i'm like I'm
yeah.
like, oh yeah, sure, that's like it's challenging, but I can do that's no that's not that's fine, I can do that, right?
Hmm.
But like that had to come from what you just said, right? Before we could do
Yes.
that, it's like, Jesus, some had to figure that out. That's insane.
Right. Right.
that's yeah, but like but that's so cool. It's like, okay, so we went from like, okay, so instead of that box having a fixed set of operations, now the box has a universal logic thingy inside, and we can program the operations that we want it to do, and we can give it data in any order we want, and we can get it out where we want, and we can have multiple of
Right.
those boxes running together parallelly, doing data things
Hmm.
parallelly. But it's the same box. Like fundamentally, it's the same box. It's just like it's just
Box.
now it's we've scaled it up, polished it up a little bit, and it's much faster. We can do more stuff with it.
Right.
That's so
Yeah.
cool.
Yeah. And yet, when you think about like all the things you're doing and where things like AI, and now we're having conversations about quantum computing
Yeah. Okay.
now.
Okay. So what is that? First of all, just like give like explain to me like I'm a 5-year-old what a quantum computer is.
Oh boy, that 5-year-old, that could
Okay,
be tough.
fine. Like a semi educated college graduate.
So just imagine, if you will, and I am not an expert, but the easiest way for me to try to explain it is, if we think about a CPU as a simple state machine using two states,
Yes.
0 and
Right.
1.
Yes. Okay.
A quantum computer is the same thing, only the state space is 0 and 1 and everything in between.
Oh. Wait, hold on.
Okay?
Is how is that like? But okay, so so far we've been talking about digital computers, right? Discrete
Hmm.
state machines, right?
Hmm.
So what about
Yeah.
analog computers? Isn't that what you're just talking about? Like something?
Well, but I can break up an analog thing into discrete pieces,
Yes.
right?
Yes. Okay.
I can think about, right? I can think about 0 and 1, but I can think about 0.25
Yes. Okay.
or
Yeah.
0.5 or
Yeah.
0.75, and now start breaking that up into even more
Yeah.
pieces.
Yeah. Yeah.
Okay? So, okay, so now I was doing a little bit of reading about it. IBM has some pretty good, stuff, with their quantum machines and stuff. I mean, the cool part is that the CPUs are about the same
Yeah.
size, silicon
Yeah.
wise, right? The problem is that you need something about the size of a car to keep it
Oh yes.
cool,
Yeah. Yeah. Exactly. Yeah.
because it has to be super
Yeah. Yeah.
cool,
Yeah. Yeah.
right? So again, what can this be useful for? Well, now it's problems that are massively scaled, where, gosh, if I can look at all these different states at the same time, now it becomes much more
Mm.
useful. And now you can it just kind of blows your mind as far as what you could kind of think about. No, I'm not going to use a quantum computer to do my word processing
Yeah.
on.
Yeah. Yeah. Yeah.
Doesn't make a lot of
Yeah. Yeah.
sense,
Yeah. Yeah.
right? Um, so this notion of, again, I mean, the notion of supercomputing, right? it's a relatively small community of scientists, engineers, and researchers that honestly understand it, that have a fairly good understanding of the types of problems that they're trying to study and
Mm.
address. With these massively parallel supercomputers, um, quantum fits kind of into the same category. I think the promise that it has is that the machines themselves can be
Yeah.
smaller, and again do
Right.
more.
Right. Right. Yeah.
So um, time will tell as to the ultimate utility of those machines. It's probably some generations away. I mean, some of the things like maybe in AI might be it might be very useful. You're studying cognition and things like that. I mean, think about um, the neural network that is the brain, the human
Mm.
brain, right? And think about, okay, what would it take to start replicating those
Right. Right.
processes? Um, Quantum might fit into that quite
I mean, it's
nicely.
always nice to
Uh,
have a new toy to play with. That's for sure.
right.
Right? Like that. Like,
So
isn't that the general idea? Is like, oh, what could possibly go wrong?
I'm right. I'm likely to go to my grave just dealing with this old binary
Yeah.
stuff.
Yeah. 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 True. Yeah.
That you know, but yeah, I mean that's kind of where some things are headed, and yeah, I mean, at the beginning of all of this, IBM said we'd sell five or six um, of these things we're calling computers, and they would go to government agencies, and they would be used to, you
Yeah.
know, study of things about weapons
Yeah.
and
Yeah.
and that sort of
Yeah.
stuff. Well, look what's
Yeah. I know
happened.
it's crazy.
They couldn't have been more wrong, and um, this whole other thing has sort of blossomed, and you get commerce involved,
Yeah,
and
for sure.
who knows. So yeah, but that's where we're headed is kind of anybody's guess, and I think yeah, with between the things that are on this planet and the things that are away from this planet, um, there's yeah, there's probably always room to grow.
Yeah.
So
Yeah. I mean, it's just
you
yeah, it's
know,
just nice. It's just great to man, it's nice. I'm hopeful. I'm generally a pretty pessimistic person. But like I just think it'll be it's gonna be fun, but it's probably gonna be dangerous, but it's gonna be fun. Like it's like a fun future, hopefully. I don't know.
well, but you're studying the right things to temper the
Yeah,
danger.
true. And but like the more I learn, the more I'm like, how am I gonna be useful? Like like how do I like? It's like, oh man, there's just so much.
It will come to you.
I hope so.
It will. It will come to
Okay.
you. All of this is going to end up converging somewhere, whether you end up in industry, in the private in the private sector, or you end up in the public sector, you end up in the academy teaching
Yeah.
others. Yeah, I in hindsight, um, I'm grateful that I was in the private sector for a fair number of years before I ever got into the academy, where I was trying to profess and impart on
Yeah.
students,
Yeah.
not only, well, here's what you can do, but here's what you need to be thinking about, as well, as you go on, because um, it's great when things work, but I mean, engineers kind of by design tend to gravitate to having an ability to find the things that are wrong with
Right.
something, right? Um, which is, it's a good characteristic, when it's tempered with a little bit of optimism that, yeah, but we can help,
Yeah, yeah, yeah,
we
yeah.
can help humanity
Exactly.
in all these, these other
Yeah.
ways, but the the being a little bit of a pessimist is actually good because you're always looking for the corner cases that can cause problems or headaches or whatever, but temper that with, well, what's the probability of that
Yeah, yeah,
happening?
yeah, yeah, yeah. True.
And
Yeah.
you can, and how much would we have to spend to eliminate
Yeah,
that?
yeah, yeah. So like, no,
If
one thing that I really, what I really appreciate about like having an engineering background is like, uh, so like like when I worked on projects on teams here, and when I talk to my colleagues, like they have all these like very idealistic sort of ideas that they want to implement. Let's say, right? Like, and what I
Mhm.
hit, and what I tell them is like there's no there, like you should, instead of thinking of things as like, okay, this is good or this is bad, it's more like, what are the costs of this versus what are the costs of that, right? There are like pros and
Right,
cons. It's like, it's not like, it's very rare that you find something that's just, oh, all good, let's go for that, or like all bad,
right,
that it's like, okay, what are the costs of this,
right,
what are the pros and what are the cons, like there's hardly ever
right.
a clear cut like good bad in engineering at
Yes,
least, right?
yes. When you develop a knack for being able to identify and articulate what the trade-offs are, so you can identify,
Yeah.
this is a, because one of the one of the three main objectives of human communication is
Hmm.
persuasion, right? I'm going to use my skills at communicating, and if it's hopefully it's evidence based, to persuade you that my story, right, is something we should
Yeah.
pursue. Okay, great. And but in being able to identify positives, potential negative, positives and potential negatives, corner cases, whatever, um, and then kind of go down the list of, well, how likely is this, going to happen? We In the automotive industry, we called it failure modes and effects
Yeah.
analysis. I hated that task. I despised it, but it was always a worthwhile kind of thing because, yeah, you'd learn really quickly that, well, if this one little wire came loose, this is the effect that it has on the engine controller. This is the effect that it has on the engine, and wow, a lot of goofy stuff
Yeah, yeah,
happens.
yeah.
So um, like with any human endeavor like this, yeah, it's important, um, to be able to develop that
Yeah,
skill of identifying and articulating trade-offs in ways that the people that are trying to make the persuasion can
yeah,
understand, and they hopefully you get to a point where someone would go, gee, I hadn't considered
yeah,
that.
yeah. So like I come across situations, even in myself, and but like a lot of people who seem who feel like they're faced with an intractable problem, but what's
Hmm.
actually happening is they have represented the problem incorrectly. It's like, because they're
Right.
asking the wrong question. It's like, okay, it's like, if you're trying to figure out what's purely good, what's purely bad, that's going to paralyze you. For example, let's say, right? It's like, okay,
Yeah.
but you have to still move forward. Okay, you have to move forward. How do you do that? Well, you maybe need a different perspective. What is the pro of this? What versus what are the cons of this? Right? Like, because you have to
Yep.
like we have to work with heuristics. Like that's one thing I learned, at least for damn sure. Like it's hard to have a optimal answer for a lot of things. You work with the most, like you you're motivated to move forward. So how the hell do you move forward if you're not willing to sort of have a more nuanced view of what needs to happen, right? You
Right.
can't be absolutist like and be an engineer. It's kind of hard.
Right. It's very
Yeah.
difficult. Yeah. You you learn that honestly, there really isn't any black and white. It's just all
Yeah.
gray, and it's where are we? Where are we in that
Yeah.
spectrum?
Yeah. Yeah,
Um,
so a lot of people have problems sort of prioritizing goals because they want to get the they want to get the optimal solution for all their goals at the same time. I'm like, dude, that's never gonna happen. Like you gotta pick something, go for one thing, and then like accept the cost. Like it's because a lot of people because I'm a bit older than I'm older than most of my colleagues. They ask me like, hey man, I'm feeling a
yeah,
bit lost. Like I find all these things interesting. I don't know what to do, and I'm like, look, all I can tell you is you gotta pick something and then pay the cost of being exceptional at the thing. Like it's a cost. You're gonna have to pay a cost for it, right? Like, what, like, but is it worth it? That's the question you gotta ask yourself. I asked my,
well,
yeah.
right, and we don't
There's this fear of missing
just
out, right?
because
This
you
fear of missing out on stuff.
right. Well, there's
Yeah,
that, and as you well know by now, right? This is a journey. The course that you decide not to
yeah,
take in a given semester, you can always get that background later if you
yeah,
find
yeah,
out
yeah,
later that, gee, I wish I would have taken that
yeah,
course, but I can do it
yeah, yeah.
now.
Exactly.
I can I can gain the knowledge in a different
Yeah,
way, but now I need
yeah,
it.
yeah, yeah.
So go
Yeah,
get
yeah,
it.
yeah, yeah. There's a way.
Right.
Like
And
it's like it's not linear at all. Like you don't have to go in one straight line. You can like it comes back. You can curve around. It's a it's
yes,
ways to get there.
yes. And you don't, the thing of it is you don't know what you're going to
Oh yeah, for
need
sure.
3, 4, 5 years
Yeah,
from
yeah,
now. So you're taking a guess in terms of what sounds interesting, what you think you're passionate about
yeah,
right
yeah,
now. And 3 or 4 years later, you may find yourself in a situation where part of the reason why you were hired was because of that background that you got back then. But now I need this
yeah,
other
yeah.
thing. Okay, go
Yeah.
get it.
Like for
You,
me, the most one of the most fun things is like that. Go get it. It's like I like that. I like that digging. I like the hunt. Like like it keeps me occupied. Like it keeps me from
yeah.
thinking about the existential stuff. It's like, okay, I have this like, okay, like I like the process of okay, here's something. So for example, I'll I'll start to read a paper in AI, and then like I'll start to read the abstract, and I'll get to like the first two sentences, and I'm like, okay, this is hard, but at least now I know, okay, I need to go learn topic A, B, C, and D before I understand this paper, so I know where to go and how to get there, right? So okay, I got to go understand
Mhm.
this part, this part, this part, and then I can come back up and read the paper. Okay, now it makes more sense. Like that process, that makes me really happy. Like that, I really enjoy that. Like if I can't do that in a semester, I get really frustrated. Like if I don't have time to like go down the rabbit hole a bit and just like see, oh okay, then I feel like I'm stretched thin. I feel like I'm like too much, like too little butter on too much bread. Like I feel like, so I feel it's
Mhm.
really stresses me out if I don't get the time to like just sit there and just stare at this thing for a little while and then go down and then get to a point where I feel intimate with the thing. I have to, like, it's a weird feeling. I feel, okay, I got you now. Then I can like take it in my arms and carry it back up and then and then go start moving forward.
Well, I mean, it's important. um, to be able to try to digest, especially some research papers with a certain level of
Yeah.
comfort that you can
Yeah.
assess the overall quality, because that researcher is going to come up, there's an abstract there, and if they've kind of done it right, it tells you basically everything that they want to
Yeah.
say
Yeah.
to
Yeah.
you,
Yeah. Yeah. Yeah.
right? And then in the conclusions, it's doing the same
Yeah. Yeah.
thing, just a little bit
Yeah.
deeper, because it's citing the stuff that's in the body of the
Yeah.
paper, right? So now if you look, abstract and then conclusions, and then determine, gee, I need to get some more
Yeah.
background so I can better process what's in the
Yeah. Yeah.
middle.
Yeah. Yeah. I'm getting better
So
at
then I can make
like
it,
that. As I do it more, I'm getting
yeah,
much better at it. Like so now, papers
yeah,
take less and less time to read. It's like okay, cool. It's nice. It's
right,
pretty cool.
right.
All right, Professor. It's been 2 hours, uh,
Yes,
and
it
this has been
has.
awesome. Every time I talk to you, it's like I have a million other questions that I want to ask. But this has been great. I'm not gonna take up any more of your time because I gotta go make dinner also. But this has been awesome.
Yeah, yeah.
Thanks.
It's good to see you
Oh,
again.
absolutely. It's always a pleasure talking to you. And thanks again for like always like it's like replying to my emails and like taking the time. I really appreciate it. It means a lot.
Oh, at any time. Your journey has been a joy to really follow.
Thank you.
It really has. It really
Oh, it's
has.
been nuts.
You know,
It's been a straight. It's been such a weird path. But like I'm feeling pretty happy about myself right now. So, um,
good.
so
That's a good
yeah,
place to
it's
be.
nice.
A good place.
Yeah, for sure.
You
Yeah,
know.
I hope we'll see how this see if I can keep this party going. And yeah,
Yeah. No, it sounds like you're on a great
it's
path.
nice. Thank you. I appreciate that.
You're on a great path. Yeah.
Cool. All right. I will
All
catch
right.
you again soon. All right.
Absolutely.
Thanks.
Absolutely. Have a great
Thank you.
semester.
I'll let you know
You
how
know.
the semester goes when I'm through with it. All right.
Absolutely.
All right.
Yeah.
Perfect.
Yeah. Counting on it.
Perfect. All right.
Yeah.
Thanks, Professor.
All
We'll see you.
righty.
Bye.
Take care.
That's a wrap, folks. I hope you enjoyed this conversation. And thanks again for listening to the One Deeper podcast. I hope you always learned something. So until next time, peace.